Hi everyone, my name is Hugo Martinez and today I'll be presenting my Lab 1 for Physics 2211, which contains all about constant velocity, and my lab section is W08. Okay, so the table of contents, this is basically me just going through what I'll be talking about in this video. So the first is my introduction, the second is the motion of car, 3 is just relative diagrams to give you a better visualization about what I'll be talking about. 4th is the prediction of car's model, and 5 will be observed versus predicted graph, and 6 will also be what does it mean, like all of this. So, okay. Okay, so introduction to premise. So basically, constant velocity comes from a net force of zero. Newton's first law of motion says that an object in motion remains in motion, and an object at rest remains at rest unless acted upon by an outside force/forces. Some formulas, again, another formula we talk about is Newton's second law. The momentum principle is that the acceleration of an object is proportional to both the mass and the net force upon the object. So some of the formulas that we had to use for this lab was F equals m times acceleration. Also, F net is equal to the change of a p over delta t. And then some other formulas that I used was the velocity update, which is v final is equal to v initial times F net over mass times the delta t. And then also the position update, which is also equal to RF is equal to RI plus velocity over delta t. Okay, so for the next slide, so an introduction for relevant information. So my system was my car, that little Hot Wheels car that I use. My surroundings is a table that's flat, that's a flat surface, and everything else like outside forces. And just a little hint of my preview result was it was mostly the same, but because some real life forces caused for the predicted results to be a little bit different, which we figured would happen. So for the motion of the car, we assume that the net force to be equal to zero because we are using a flat surface, and there is no acceleration/change in momentum for the car. So moreover, this gives us that v final is equal to v initial, which is our velocity average. So here's a picture of tracker, and I use this to get all my data here on the right, and then I figured out that initial velocity can also be the change in R over the change in t. And then my initial conditions, well, I use that with a tracker to find out those exact conditions I need to figure out what to manipulate it with all the formulas. And I use the weight scale to get the mass of my car. So moving forward, some relevant diagrams. So here's a picture of my car. So you can see here on the left side, up on the top there would be normal force, but if you had like an applied force and then gravity, this would be a ball with increasing speed. If you had normal force up top and then gravity just working its thing, then you would have a ball at constant velocity. Okay. All right, so prediction of the car's motion computational model. So here is my Glowscripts code. Basically, what I had to change was the mass, obviously, position equal to 0, 0, 0, and then also my velocity using the formulas that I had mentioned before. Okay, and then also used the force net equal to 0. Obviously, we needed to change that as well. And, okay. So here's where I implemented the formulas. And, I followed the Glowscripts code, show me what I needed to do, and implement the formulas to give me an exact value of what I wanted for my lab. And it all begins with the first phase of my introduction, like using those formulas to manipulate the Glowscripts code and getting all these values that you need to implement for that for the code. Oops. Okay, so observed versus predicted graph. So you can see here that I have a green line equals computational model, red line equals tracker. So tracker was a little steeper. That's definitely due to some human error and then some of the stuff that maybe I could have messed up or anything like that. But the computational model is a linear line because no force is acting upon that. So errors would be like the real world net force, which is not equal to 0, such as friction and for all this stuff of the video that stopped the car. And my measurements may be off by human error as well. Okay, so what does it mean? So I'll speed through this quick. So basically we had these questions in our lab report to analyze, and to answer the questions on this video is first, flipping the axis, it would only change the slope, but wouldn't change the overall conclusion from the model as much. The differences in the model is due to human error and outside forces. And then for my second answer, I put for the given model, there isn't enough information to determine how many forces are acting on the car that would give that zero net force. Like we have just so many things that we could include from. So that would be my final conclusion. And all right, so that's the end of this video, and I hope you all enjoyed. Thanks for watching.